Welcome back to the deep dive. If you're here with us now, it probably means you've already taken that first pass. You've gone through the essentials, you know the names, persistent disk, cloud storage, file store. You've seen the basic architecture diagram.
Right, the one-on-one level stuff.
Exactly. But you also know that moment when you move from the basics to, actually trying to design something real. And all those concepts that seem so clear suddenly get a little, well, a little fuzzy.
That's the perfect word for it, fuzzy.
Yeah.
Because the real challenge in mastering cloud storage isn't just memorizing definitions. It's about differentiating between these services that, on the surface, seem to do pretty similar things.
Like storing files.
Right. I mean, persistent disk stores files. File store stores files. They sound like they should be interchangeable, but they serve fundamentally completely different needs. And that's our mission today. We want to solidify that intermediate understanding.
This is the second view.
This is absolutely the second view of the source material. We're moving beyond just the what, and we're really going to dig deep into the why.
We're going to explain why one choice might be the absolute cornerstone of your regulatory compliance strategy, while another, almost identical sounding service, would be the worst possible choice for that same audit archive.
And we are focused. We are solely in the storage domain today. We're not going to get sidetracked by, complex networking details or some specialized compute configurations.
Right.
This is all about mastering the landscape of block, file, and object storage. And just as importantly, the critical tools you use to manage their costs, their security, and their longevity.
So what's the mental model for this? What's the analogy we should be holding in our heads?
The best one we've found from looking at all this is to stop thinking of cloud storage as just one giant magical hard drive in the sky. That model breaks down really fast.
Okay.
Instead, you should think of it as a collection of highly specialized storage facilities. Each one is built for a specific purpose.
I like that. So like different kinds of buildings.
Exactly. You've got your temporary super high-speed workbench right next to you. That's your local SSD. Then you have your personal, reliable storage locker that you own. That's your persistent disk.
Mm-hmm.
Then there's the shared community filing cabinet where everyone can access the same drawers. That's FileStore. And finally, you have the massive global archival warehouse, the size of a city block.
Yeah.
And that's cloud storage.
And choosing the right facility for the right job, that's the whole game. That's the difference between an elegant, cost-effective architecture and, well, one that just hemorrhages money and hits performance walls every single quarter.
That's the entire game.
Okay, let's get into it. Let's unpack this by diving into those three pillars that really define this whole world.
Let's do it. And we have to start with speed, because in terms of raw I/O performance, there's just nothing that beats local SSD.
Local SSD. Okay, we know the name, but let's really quantify that performance.
Right.
And more importantly, let's define scratch space. Because that temporary nature is, it's defining feature, but it's also its biggest warning label.
It really is. It's the absolute pinnacle of speed because it's physically tied to the host machine. We're talking about the actual server that is running your virtual machine in the data center.
So no network in between.
Zero network hops. It's NVMe-based flash storage. And it offers just ridiculously low latency because you're completely avoiding the network trip that's inherent in all the other more durable, persistent solutions.
There's the catch.
There's the big catch. The limitation is non-persistence. If that underlying compute instance is stopped, or if the host machine has a failure and your VM gets restarted somewhere else, the data on that local SSD is gone. Poof.
Mm-hmm.
It is completely volatile.
Okay, so that's a huge risk. If the data just vanishes when the instance stops, why would any architect ever choose this over a persistent disk, which, guarantees persistence?
Because there are specific, very important scenarios where the need for speed so dramatically outweighs the need for persistence that it becomes the only logical choice. And the best example the source material gives for this is training massive machine learning models.
Okay, now this is where it gets really interesting. Let's quantify that requirement. Why does an ML model demand this specific and, frankly, risky type of storage?
It all comes down to one metric, IOPS, input-output operations per second.
Right.
When you have a deep learning model that's running, millions of iterations, and it's constantly reading and writing these intermediate results, these tiny little files, any fractional delay in accessing that data adds up. It translates to hours or even days of wasted training time and money.
So what's the difference in IOPS we're talking about here? Give us some numbers.
Okay, so if you use a standard network persistent disk, even a really good one, an SSD-backed one, you might get performance in the range of, say, 15,000 to maybe 30,000 IOPS on a standard setup. And that's good. That's fast for most things.
15 to 30,000.
Yeah.
Okay.
But it's not fast enough for these massive parallel workloads. With local SSD, we are talking about an entirely different magnitude,
A different league.
a completely different league. Depending on how many of these local SSD drives you physically attach to that machine, you can potentially hit hundreds of thousands, sometimes even a million IOPS.
Wow. Okay. A million.
Yeah, and that sheer jump in performance is what allows these complex multi-terabyte training data sets to be iterated over quickly. The data it's accessing is temporary. It's just a scratch pad for the calculations.
So the working data can be erased.
Exactly. The model checkpoint itself,
Yeah.
the final validated result of the training run, that gets saved out periodically to a persistent store, like cloud storage. But the working data, the scratch pad, you can afford to lose it.
So the performance justification just completely trumps the persistence requirement as long as you have a system built in to save your final results somewhere safe.
That's the discipline.
The analogy holds up then. If you're a master chef, you need the biggest, fastest, most expansive workbench right next to your station to prep ingredients, even though you know you're going to wipe it completely clean at the end of your shift.
Absolutely. You would never put your family photos on that workbench. You only put data there that you can afford to lose or that you know has already been securely backed up somewhere else. If your entire application relies on the stability of that data surviving a restart, local SSD is a total non-starter.
Okay, so from the most volatile, let's move to the most common, the workhorse.
The workhorse of cloud computing. We're moving away from the volatile nature of local SSD, and we find persistent disk, or PD. This is your standard block storage.
And this is what most people are familiar with, right? It's the default C drive, the virtual hard drive for your VMs. It gives you reliability, it gives you persistence. But let's clarify the technicals. Why is it called block storage? What does that actually mean?
It's called block storage because that's the level at which the underlying operating system kernel accesses the data. It sees the world in these fixed, standardized chunks called blocks. The OS treats this storage as if it were a local physical hard drive plugged right into the motherboard,
Even though it's not.
even though it's actually networked. And that network connection is the magic that allows for the persistence.
Okay, that distinction is crucial. Tell us more about that persistence mechanism. How does it work?
So, because the storage is networked, it's decoupled from the specific compute instance, from your VM. So if your VM crashes, or if you intentionally stop it, or if you decide to migrate it to a different host machine for maintenance,
Right?
the persistent disk is simply detached, and then it can be reattached to the new instance almost instantly. The data remains completely intact, it's reliable, and it's available. And that's why it's the standard for VM boot volumes, for operational data, for basically any application that requires guaranteed data survival past a machine restart.
But the documentation we reviewed, it flags a specific challenge, even for PDs. High-performance database backups. You mentioned that even a reliable, high IOPS persistent disk can really suffer if you try to run a big MySQL dump directly onto it. Why the complexity?
Yeah, this is a great real-world example. If you're running a high-transaction database, that persistent disk is already busy. It's handling all the incoming reads and writes for your live traffic from your users.
It's already doing its day job.
It's already working hard.
Yeah.
So when you kick off a major database dump, which involves reading the entire database contents and then writing this one massive file, you were just saturating the I/O capacity of that PD. It creates a traffic jam. And the result is latency spikes for the live application. Your users feel it.
So the recommended practice detailed in the sources, it mitigates this by adding this complex-sounding intermediate step.
It sounds complex, but it's really elegant. You temporarily mount a local SSD volume or scratch pad onto that database server.
So you bring in the speed daemon for a special job.
Exactly. You direct the high-speed MySQL dump to write to that temporary hyperfast location. By doing that, you minimize the impact on the primary PD because of the big, heavy write operation is going to this dedicated local SSD. It's not competing with user traffic.
And then what happens to the dump file?
Once the dump is complete, you then use a simple copy utility, something like a scratchpad, to move that finished backup file from the scratchpad into long-term cloud storage for safekeeping.
That one process perfectly illustrates the whole storage hierarchy. You have PD for the live stable data, local SSD for the raw burst performance you need for the backup, and then cloud storage as the final scalable destination.
And that ties directly into the major constraint of persistent disk. It's designed for single ownership. PDs are, generally speaking, not designed for concurrent read-write sharing across a big fleet of VMs.
What happens if you try?
If you have, say, 10 or 50 different servers, all trying to access the exact same underlying file system on that one PD at the same time, you are just asking for trouble. You risk data corruption, you risk system instability, because the underlying block access layer just doesn't have the necessary file locking mechanisms to coordinate all that activity across multiple separate operating systems.
She doesn't know how to manage the chaos.
It has no idea.
Huh.
So if sharing is the requirement, you absolutely must move to the next pillar.
Which brings us to FileStore. So now we're moving from individual hard drives, which is block, to what feels more like a shared network drive. And the defining technical concept here is PO6 compliance. Can you explain what PO6 means and why, for some applications, it is absolutely non-negotiable?
Right. BIOS 6 stands for a Portable Operating System Interface, and it's basically a set of standards that governs how operating systems, typically your Unix and Linux flavors, interact with file systems.
Okay.
And, crucially, it defines the standard commands for operations like opening files, reading data, and, most importantly for this conversation, file locking.
Okay, file locking. Why does that specific feature matter so much when you have multiple systems all trying to get to the same data?
Well, imagine you have 50 VMs all running a legacy application that simultaneously tries to write to the same configuration file or the same log file.
Right, a race condition.
A massive race condition. Without a robust, managed file locking system, which is what a POCX compliant system provides, you get chaos. You get corrupted data, you get application failures. Persistent disk just can't handle this because it's designed for block access by a single OS.
Yeah.
It doesn't speak that language.
So FileStore is providing a managed NFS mount, a network file system that handles all that complexity for you.
It handles it behind the scenes. It ensures that the application, which was probably written, 10 years ago, assuming it would be running on a traditional on-premises network share,
Right.
works perfectly without modification in the cloud environment.
So the value of FileStore isn't just the storage itself. It's the seamless managed provision of these concurrent access and file locking protocols that older applications just have to have.
Exactly. The source material highlights two scenarios where this is absolutely essential. The first one is pretty straightforward, that legacy app migration. You have a fleet of, say, 50 web servers, and they all need to read and write to the exact same shared directory of images or session files at the same time. Block storage fails completely there. Fails completely. But FileStore succeeds. But the second scenario is even more illustrative of the raw power that's required here. High-performance computing, or HPC.
Right. This is the big stuff.
This is the really big stuff. We're talking about HPC workloads like cinematic rendering farms, complex financial modeling, seismic simulations. These can consist of potentially hundreds of compute nodes that all must pound the same data set concurrently.
All at once.
All at once. They need that PSX compliance for the file locking, but they also require astronomical throughput. We're often talking about multiple gigabytes per second, GBs.
Wow.
This is sustained parallel performance where any data starvation, any delay means a massive loss of incredibly expensive compute time.
That sounds incredibly demanding. And I know FileStore costs significantly more per gigabyte than a persistent disk or standard cloud storage. So why wouldn't I just, try to build my own shared file system on top of a persistent disk and save some money?
That's the conflict every architect faces. And you could try to manage that complexity yourself. You absolutely could.
But
But the cost of the specialized hardware you'd need to handle that concurrent I/O at scale, plus the immense administrative overhead of configuring it, patching it, maintaining that file locking cluster, it almost always outweighs the managed service cost in the long run.
the total cost of ownership.
The TCO is just brutal. And for those highest performance needs, those multi-GBs workloads, you skip the basic tier of FileStore entirely. You go straight for the high scale or enterprise tiers, which are explicitly engineered for that massive throughput and low latency sharing across hundreds or even thousands of clients.
So FileStore is the premium solution. It's for when the ability to concurrently share files using standard OS commands is a foundational, non-negotiable requirement of the application.
Absolutely. And that brings us to the final pillar, the massive scalable destination that is cloud storage. This is object storage, and it operates under a completely different set of rules than the previous two.
Let's break that down. Object storage. How does it fundamentally differ from file or block storage?
Well, in block and file storage, your data is organized in this hierarchical file system, with folders and subfolders. You access it by mounting a volume.
Like a drive letter.
Exactly. In object storage, data is stored as a distinct, self-contained unit. We call it the object. And that object contains the data itself, plus all of its associated metadata, all bundled together.
And these objects are stored in
They're
buckets.
stored in containers we call buckets. And crucially, you don't access these objects with a file path like c foldingfile.txt. You access them via a unique HTTP API endpoint. It's more like a web address.
So it's designed for the web, for internet scale access. It's massive, it's durable, it's highly available. It's built to hold petabytes of data without even breaking a sweat.
That's it. It's the ultimate repository for anything that needs to exist long term, but doesn't need that millisecond latency file system level access that FileStore or PD provides.
So that's the T trade-off.
That is the trade-off. You get near infinite scale and incredible durability. We're talking typically 99.999999999% durability, 11 nines.
11 nines, that number is just, it's hard to even comprehend what that means.
It basically means that if you store 10 million objects, you can expect to lose one of them roughly every 10,000 years. It's incredibly durable. But you sacrifice the low latency of local SSD, and you give up the shared file locking capabilities of FileStore.
So give us the classic use cases outlined in the sources. What goes in this giant warehouse?
They really fall into two major categories. First is archives and backups. Think long-term log archives. The sources cited an example of 20 TB of logs being retained for legal reasons, or image libraries for a website, disaster recovery backups, static assets like CSS and JavaScript files.
What's in the second category?
The second, and maybe more powerful category, is integration with big data and analytics. Cloud storage basically acts as the staging ground for massive data lakes.
Okay, that integration is the bridge. That's what takes it to the next level of cloud architecture. Tell us about the combined steps for doing something like log analysis.
Right. When you're dealing with massive log volumes, terabytes, or even petabytes, you can't analyze them directly on a VM. So the first step is always to upload those raw log files directly into a cloud storage bucket.
You just dump them in there.
You dump them in there. Once they're there, the second step is to load that data from the bucket into a robust analytics engine like BigQuery for analysis. Cloud storage provides that durable, economical, and highly parallelizable access layer that's necessary before these specialized analysis tools can get to work and process the data.
Okay, so to quickly summarize this first section, which is really the cornerstone of our whole deep dive, local SSD is your ephemeral, nitro-fueled speed booster.
Right, your scratch pad.
Persistent disk is your reliable, single-instance workhorse. FileStore is your managed, shared PO6 environment for those tricky concurrent apps.
The shared filing cabinet.
And cloud storage is your massive, durable object warehouse. And knowing those distinctions is what allows you to then move into managing the life cycle of that data effectively, which is all about cost.
All about cost and compliance.
We've established the right place to put our data based on speed and file type, but once the data is in the cloud, the biggest recurring operational headache is always the budget.
Always.
Data is rarely accessed at the same rate throughout its life, and if you don't manage its transition from, hot to cold, you just hemorrhage money on storage costs.
And this is the critical juncture. This is where the intermediate architect really distinguishes themselves from a beginner. Because doing this manually is impossible to scale.
Yeah.
You can't have someone moving files around every day. This is where object lifecycle management rules become your automated cost saver.
Okay, before we get to the rules, let's start by defining the cost structure that drives them. Cloud storage offers these different tiers: standard, nearline, coldline, and archive. What differentiates them beyond just the monthly storage price?
There are three main factors you have to look at. There's the storage cost per gigabyte per month, there's the retrieval cost, and there's the retrieval latency.
Okay.
Standard is the most expensive to store, but it has zero retrieval cost and millisecond latency. It's for hot data you access all the time. But as you move down that ladder to nearline, coldline, and archive, the storage cost drops dramatically.
But new costs appear.
Right. Two new factors appear. First, there's a retrieval cost. You actually pay a small fee per gigabyte to access the data. And second, there's a retrieval penalty or latency.
Give us an example of that latency penalty. What does it feel like?
For nearline, it's still pretty much millisecond latency, so it feels fast. But for coldline, retrieval might take a few minutes for the data to become available. And for archive, it could potentially take hours. You have to factor in that time delay.
And there's one more catch, right? The early deletion thing.
Yes, the early deletion charge. This is a big gotcha. Nearline, coldline, and archive all implement this. If you delete a file before its minimum retention period, like 30 days for nearline, 90 for coldline, you still pay for the storage for that full period.
So you can't just use coldline as a temporary dumping ground.
No. The whole structure forces you to accurately predict your data access patterns. It rewards planning.
Okay, so that's the financial landscape. Now, let's look at how lifecycle rules automate this planning. The sources show this is done with a JSON rule.
Yeah, the rules are basically just a set of if-then statements. You define them in a JSON file, and then you push that configuration to the bucket using a command line tool like SUSE.
And what can they do?
They monitor properties of the objects like their age or their current storage class, and then they trigger actions. The main actions are transition to a new class or simply delete object.
Okay, let's apply this to that classic scenario we saw earlier, the log retention requirement. So we have 1 TB of logs being generated every single day. They have to be actively queried for 30 days, but then they have to be retained for an audit for 2 years.
This is a perfect two-step lifecycle rule, a textbook case. So step 1, for that first month, they're being actively queried, so they land in the most expensive but most responsive class. Standard storage.
Hot storage.
Hot storage. Then, after 30 days, the first lifecycle rule triggers. It sees that the object is 30 days old, and it automatically transitions those files into cold line storage.
And why cold line specifically? Why not nearline or archive?
Well, cold line satisfies the retention requirement perfectly. Its storage cost is extremely low, which is what you want for the next 23 months. And since the data is only needed for a potential audit, a retrieval latency of a few minutes is perfectly acceptable. You don't need instant access.
So this one automated transition rule lets the company satisfy that 2-year retention policy while just dramatically minimizing the cost.
Dramatically. Without that rule, you'd be paying the high standard storage rates for all 24 months. And across terabytes and terabytes of logs, that is a significant and completely unnecessary financial difference.
So lifecycle management is the core mechanism for optimizing your ongoing spend. But we also need to talk about auto class. It sounds like the easy button if you don't want to define all those rules yourself.
It is kind of the easy button. Auto class is the hands-off approach, and it's designed for inconsistent or unpredictable access patterns. You just configure the bucket once, and the system does the work.
What does it do?
It monitors how frequently each individual object is accessed. If an object hasn't been touched for a long time, the system automatically transitions it to a cheaper storage class for you. But if that same object is suddenly accessed frequently, it automatically moves it back to standard.
It sounds like it removes the whole administrative headache. Is there a downside, a cost to that convenience?
There is. While it saves you the complexity of defining dozens of rules, AutoClass does charge a small monthly management fee per object. And it might not be as perfectly cost-optimized as a very well-planned, manually defined lifecycle policy if your access patterns are perfectly consistent and predictable.
So if you know exactly what's going to happen, do it yourself.
Right. But if your traffic is all over the place, sometimes hot, sometimes cold, and you just need reliability without having to think about it, AutoClass is an excellent choice.
Okay, so that's saving money. But what about staying out of legal trouble?
A different and often more important problem. When regulations mandate that data cannot be altered or deleted for a fixed period, and that means regardless of user intent or even administrator actions, you need something much stronger than a lifecycle rule. You need compliance-driven storage.
This brings us to that crucial concept of worm. Write once, read many. The sources cite real-world examples for this. Financial data, like mortgage loan approvals that have to be retained for 5 years, or specific video surveillance files that have to be retained for 7. The data must be demonstrably immutable. You have to be able to prove it wasn't touched.
And your standard IAM policies just aren't good enough here. IAM is great, it controls who can do what, but a powerful administrator with sufficient permissions can always change those policies.
So they can give themselves permission to delete.
Exactly. The only feature that provides true regulatory-grade immutability is the cloud storage bucket lock with a retention policy.
Walk us through the mechanism of that lock. Why is it so powerful? What makes it different?
So you first set the retention policy on the bucket. For instance, you say, everything in this bucket must be retained for 5 years. Then, and this is the critical step, you lock that policy using the bucket lock feature.
And once it's locked,
that policy becomes permanent and unbreakable for the duration you set. This ensures that the documents in that bucket cannot be deleted or overwritten by anyone. Not project owners, not company administrators, and certainly not the storage service itself. They're locked in until that 5-year clock runs out.
I have to challenge that, though. Let's say a company sets a 7-year lock, because that's the regulation. But 3 years in, the regulatory body changes the requirement down to 4 years. Can they get out of it? Can they call support and have it unlocked?
No, and that is the entire point. That is the core of regulatory compliance. Rigidity. The point of a lock is that it must be unbreakable for the period defined, otherwise it would fail an audit. The whole system would be meaningless.
So there's no escape hatch.
The only way to bypass the lock is if the bucket is not yet locked, or if the retention period is extended. You can always make the policy longer. You can change a 5-year lock to a 10-year lock. But you can never make it shorter, and you absolutely cannot delete the objects before their term is up. That non-negotiable rigidity is what satisfies strict compliance requirements like FINRA or HIPAA.
That makes the distinction with object versioning crystal clear. I think a lot of people confuse the two.
They do?
So versioning is for recovery, but bucket lock is for regulation.
That's the perfect way to put it. Object versioning cracks every change and every deletion, and it allows for operational rollback. If you accidentally overwrite an important file, you can just retrieve the previous version. It's a fantastic protection against human error.
But it's not a compliance tool.
No, because
Yeah.
the current object and all of its previous versions could, theoretically, still be subject to deletion or transition by a powerful user if it's not also protected by a stringent retention lock. If immutability is the goal, the lock is the only feature that matters.
Okay, we know where the data should live, and we know how to manage it once it's settled in. But for so many organizations that are moving to the cloud, the very first hurdle is just how do we get our massive amounts of data from our on-premises data centers to the cloud in the first place?
The migration strategy.
We need to talk about migration strategy and the true cost of bandwidth.
Yeah, bandwidth is the silent killer of migration timelines. It's so common. People hear, oh, we have a 1 Gbps connection, and they think, that's plenty fast. But when you actually start calculating the time required to move massive data sets, the limitations become terrifyingly apparent.
Let's put that into perspective for you listening. A 1 Gbps connection theoretically moves about 10 terabytes of data in a little over 22 hours. And that's assuming perfect utilization, zero overhead, which never happens.
Never. In reality, with network jitter, API overhead, protocol acknowledgements, you're often looking at significantly more time. Maybe 30 hours, maybe more.
So if you're trying to move 10 TB and you only have a 2-day maintenance window to get it done, a standard single-threaded upload is probably going to fail.
It's very likely to fail. And this is why optimization is critical, even for what we might think of as medium volumes.
Okay, so let's take that medium volume migration, say, a 10 TB database export. Time and database load are the priorities. The recommendation we saw is pretty straightforward. Compress the data, and then use the GNU-Calim ASM flag. Why is that specific flag, the NM, the key to success?
The NM flag stands for multi-threaded. When you upload a massive file or a folder with many small files using GNU-Catil without that AM flag, the process is serial. It sends one API request for a chunk of data, it waits for the confirmation that it was received, and then it sends the next one.
One at a time.
One at a time. It's very polite, but very slow. The NM flag tells the utility to just open up the fire hose. It initiates multiple parallel API calls simultaneously.
So it's chunking the data up and just blasting those chunks across the available bandwidth all at the same time.
That is exactly the mechanism. It'll split a massive file into numerous smaller components, and it sends them all concurrently. And this ensures that the bottleneck is the pipe itself, your 1 Gbps link, and not the single-threaded upload client on your server.
And the result is that it minimizes the time the on-premises database has to be running that export process, and it drastically cuts down the overall migration window.
It's a game changer, and it highlights a core principle of the cloud. Often, the most powerful tools are these optimized command line utilities that are designed from the ground up to maximize parallelization.
Okay, but optimization only works up to a point. Eventually, the volume of data becomes so massive, or the available bandwidth is so poor, that the whole calculation just tips entirely. Our sources presented a scenario for moving 75 TB of data. At that level, a network upload is just prohibitive.
It's a non-starter. And this is that critical tipping point where we have to revert to the oldest migration protocol in human history, shipping something in a box. This is the transfer appliance.
Right. Sometimes the fastest protocol is still FedEx.
It truly is. For volumes of 75 TB, 100 TB, or even more, especially if you have very poor or unreliable connectivity, shipping a physical device is the recommended practice. It completely bypasses the network constraint.
So what exactly is the transfer appliance? I mean, it's not just a consumer hard drive you buy at the store, right?
No, absolutely not. It's a ruggedized, highly secure server device that's provided by the cloud provider. The process involves several very rigorous steps to ensure security and reliability.
Walk us through it.
First, the appliance is shipped to your on-premises data center. You then copy the 75 TB of data locally onto the appliance, which has mandatory built-in encryption protocols. The data is encrypted before it's even written to the drives on the appliance.
Okay, so it's secure from the get-go. And what happens once the copying is complete?
You then return the physical appliance via a secure tracked logistics provider. Once it arrives at the designated Google facility, a special tool called the Transfer Appliance Rehydrator takes over. It securely decrypts the data and then uploads it at very high speed directly into your specified cloud storage bucket.
And the cost justification here must be immense. When you factor in the cost of time, the potential for network interruptions that force you to restart the whole upload.
And the egress bandwidth, charges from other cloud providers, or even just the internal cost of saturating your own corporate internet link for weeks on end.
Right. The fee for the transfer appliance and its logistics becomes dramatically more cost-effective.
It's not just about speed either. It's about reliability and compliance. Trying to move 75 TB over a flaky 100 MB piece link could take months, and it would likely fail and have to be restarted repeatedly. The physical method guarantees that the encrypted data will arrive securely and be ingested, mitigating both the network headache and the reliability constraint entirely.
So getting the data there is a huge victory. But the battle isn't over until we verify its integrity and we secure who can actually access it. Let's look at the security nuances for high-volume storage.
Right, so you've just moved 100 TB of critical medical imaging data. You have to be 100% certain that the file that landed in the cloud is an exact, uncorrupted, bit-for-bit match of the source file on-prem.
But the problem is, downloading 100 TB again just to run a comparison is incredibly expensive in terms of egress costs, and it's incredibly time-consuming.
We need a much more efficient, cost-minimized method for verification, and the sources point us directly to CRC32C hashes.
CRC32C. Let's break that down.
It stands for Cyclic Redundancy Check. Specifically, it's a 32-bit version that uses what's called the Castagnoli polynomial. But you don't need to know that. What you need to know is that it's a highly efficient algorithm for detecting accidental data corruption. It generates a small, unique digital fingerprint for the file based on its content.
Okay, so walk us through the practical application of this using Sutil. How does this brilliant shortcut save us from those huge egress costs?
It's a simple three-step process, and it's designed specifically to eliminate the need for costly data egress. So, step 1. Before you even start the upload, on your local on-premises server, you use the command gstool-ac and then the file name.
Okay.
This generates the CRC32C hash of the local file. You copy that hash and save it somewhere. Step 2. After the upload is complete, you use a different command, gsutil-ls-ll, and then the path to the object in the bucket. The -l flag is for long listing, and it shows all the properties of the uploaded object.
And one of those properties is the hash.
Exactly. Crucially, cloud storage calculates and stores its own CRC32C hash of the object as it receives the data. The cloud provider gives you the fingerprint that it calculated on its end.
So you got two fingerprints.
You got two fingerprints. And step 3 is you just compare them, the one you generated locally and the one the cloud provider calculated. If they match, you have cryptographic assurance that the file is identical and uncorrupted. You've just verified 100 TPA of data without ever having to move a single byte back down across the wire.
That's mastering the toolset. It's not just knowing the command exists, it's understanding that the infrastructure is running that check for you automatically and enabling that incredibly cost-effective validation.
Precisely. Next, let's address data sensitivity and those regulatory mandates around encryption keys. Many industry regulations, especially in finance and healthcare, require that the key used to encrypt sensitive PII, personally identifiable information or financial data, must be rotated on a regular schedule.
Right, sometimes quarterly, sometimes annually.
So this requires not just strong encryption, but strong key management. And a core security best practice is to keep your key management separate from the storage itself. You don't want the keys to the kingdom stored in the same room as the treasure.
So what's the tool for that?
Cloud Key Management Service, or KMS. The best practice is to leverage the specialized service that is designed explicitly for managing cryptographic material. You create the key inside KMS. You define its rotation schedule, its access controls. Then you go to your storage bucket and you set its default encryption key to use that specific Cloud KMS key.
And the big advantage there is centralized control and enforced automated rotation.
Precisely. By linking the bucket's encryption to a KMS key, the platform handles all the encryption and decryption on the fly, transparently, but you retain complete control over the key's lifecycle. You can audit who accesses the key, you can automatically enforce rotation, and you can satisfy those demanding regulatory requirements far more easily than trying to track and update keys manually across dozens of different storage resources. It keeps the data separate from the secrets used to protect it.
We should probably also mention the alternative, which is customer-supplied encryption keys, or CSE. When would someone choose to take on that extra responsibility?
CSE is really for customers who have an extremely strict requirement to maintain complete physical control over their keys, maybe due to highly unique or specific internal corporate
Nice
policies.
of work.
You supply your own AES-256 key via a configuration file like a .boto file, or as a command line flag every time you upload or download data. The advantage is maximum control. The key literally never leaves your domain.
But the disadvantage?
The disadvantage is that you are now entirely responsible for everything: key rotation, key backup, secure key distribution. It's a significant operational burden that most users are very happy to avoid by choosing a managed service like KMS.
Okay, so that brings us to the final piece of the puzzle: access control. And this can be confusing because cloud storage offers three distinct methods for granting permission. And using the wrong one for the wrong situation is a really common architectural flaw.
It's so common. We need to clearly define when you should use signed URLs, when you should use IAM, and when you should use ACLs.
Let's start with the one that's designed for external temporary access: signed URLs. What is the ultimate restriction, the defining feature here?
The time constraint. A signed URL is designed specifically for sharing a private object with an external user who does not have a Google account, and where that access must be valid for a very limited time. We're talking 15 minutes, maybe 4 hours.
So this is critical for security. It's not a permanent link you can just pass around forever.
No, absolutely not. You are essentially baking a temporary authentication and authorization token right into the URL itself. And this means you could distribute a highly sensitive file, like a contract, to a vendor or a client for a brief window of time without having to provision them full cloud credentials or IAM roles. Once that time is up, the URL is just a useless string of characters.
It's a single-use, time-stamped key pass.
Perfect analogy. Now, let's move to the standard long-term mechanism: IAM policies and roles.
This is the modern way.
This is the modern bedrock of cloud security. IAM is all about defining permissions for identified entities: actual users, service accounts for applications and groups. In the storage world, you might grant a specific service account the object writer role so it can upload logs. This is for long-term structural permissions. IAM controls access at the project, or more commonly, the bucket level, which simplifies management significantly.
The source material specifically mentioned uniform bucket-level access in relation to IAM. Why is moving towards that uniform access considered a best practice?
Uniform bucket-level access means you enforce your IAM policies consistently across all objects within that bucket. There are no exceptions. This massively simplifies auditing and it reduces complexity. It's the modern scalable approach to security because you manage all your policies centrally, using roles instead of worrying about individual files.
Which brings us perfectly to the third method: ACLs, or access control lists. If we have IAM, which is the modern preferred way, why do ACLs still even exist?
Legacy, mostly. ACLs are the older, much more fine-grained access control system. They allow you to set permissions on individual objects within a bucket, separate from or in addition to the bucket's overall IAM policy. Historically, ACLs allowed for this very granular control.
But they create a mess.
They create a massive administrative overhead because now every single object could potentially have its own unique security configuration. It becomes impossible to audit or reason about who has access to what.
So if I upload 100,000 log files and for some reason 10 of them require unique permissions that are different from the other 99,990, I might be forced to use ACLs, but otherwise I should always stick to IAM.
That is absolutely the architectural preference today. If you need hyper-granular object-by-object control, ACLs are the mechanism that provides it. But for the vast majority of environments, security teams overwhelmingly prefer the simplicity, the auditability, and the central control provided by IAM through uniform bucket-level access. You should only really revert to ACLs if there is a demonstrated unavoidable need for that per-object permission differentiation.
Okay, so to sum up access control: temporary external access, signed URL, long-term organizational permissions for your own people and apps, IAM roles, and granular object-by-object access. ACLs, but use them sparingly.
You've got it.
We've covered a lot of ground today. We moved from the fastest, most volatile components all the way to the most durable compliance mechanisms. Let's try to synthesize the foundational decisions here.
It really all comes down to selecting the right tool for the job based on the application's core requirement. Storage mastery is about that selection process. You're choosing local SSD when you need raw speed, and you can accept volatility.
Right.
You're choosing persistent disk for reliable single-instance block storage. You use FileStore when you have that non-negotiable demand for concurrent shared POSIC access. And you use cloud storage for massive, durable object archiving and as a staging area for analytics.
And crucially, mastery also means understanding the constraints imposed by the real world. Bandwidth determines if you spend your time maximizing network utilization with key sutil M, or if the sheer volume of data forces you to physically ship it via the transfer appliance.
And compliance dictates your next move. It determines if you just need simple, cost-saving lifecycle rules to transition data to cold line, or if you need the non-negotiable immutable wall, that is the bucket lock retention policy.
Every choice has consequences, in performance, in cost, and in risk.
And understanding that matrix is really what turns an essential level user into a true intermediate architect.
And that brings us to our final provocative thought for you to take away. We noted earlier that high-frequency storage scenario that was described in the sources, handling 3,000 event records per second and saving every single one of them to cloud storage.
A massive write load.
A massive parallel write load. And to manage this across a single bucket, the sources recommended a file naming convention that included compression, metadata, and most interestingly, a random prefix pattern for the file names.
That random prefix pattern is such a subtle but profound detail when you start dealing with storage at a very high volume.
So for you, the listener, to consider, what is the hidden cost of high-frequency storage operations in a single bucket? When thousands of services are all trying to write new files simultaneously, cloud storage buckets, despite their incredible scale, can experience contention or bottlenecks in their underlying metadata service. This happens especially if all the new writes are trying to operate within the same alphabetical region of the bucket's index.
We call that hot spotting.
So the question to mull over is, what role does that random prefix pattern play in distributing that load, in spreading the writes across the entire index, and ensuring the efficiency of those massive parallel writes across the platform? That's a concept of advanced scale and optimization to think about as you design your next high-volume system.
A great place to leave it.
That's it for this deep dive. We hope we've helped you move past those fuzzy ideas and really solidify your foundational concepts.
Thanks for diving in with us.